Hello my dears, how are you all? So today we are going to discuss a very important session in KCB sub-engineer syllabus regarding electronics, which is nothing but UJT or Unijunction transistor. It's very important. So normally the many questions actually asked, and especially regarding the application and regarding where it is used and regarding especially the symbol. The symbol is very important, my dear. So let's look into what is exactly or what is meant by this UJT in very detail. See my dears, UJT as the name indicate, it's a three-terminal device. It's a three-terminal device, my dears. Three-terminal device, and its full form is nothing but Unijunction transistor. What is that? Unijunction transistor. As the name indicate, this UJT consists of only one junction. This UJT consists of only one junction. I will tell you what it is. This is a structure of a UJT, my dears. This is a structure of a UJT. The UJT consists of one P region, a small P region, and a very big N region. This is nothing but the silicon N-type bar. No? This is N region hole, and there is a PN in between this P and this whole big N. And this P region is considered to be the emitter region, and the whole N region is actually divided into two bases. First base is nothing but base 1 B1, second base is nothing to, my dear, base 2. Okay, and this base 2 is nothing but very near to this P. Base 2 is very near to this P. That is, you have to remember. So first of all, this is the structure and this is the symbol. This symbol is very important. You have to know this symbol. We have to know this symbol. Okay, that's all. And let us see the working, or let's see the operation. That is very important. See my dears, so the consideration for the operation, first you have to consider for no voltage across this emitter, or when the emitter is open. When the emitter is open, we apply a VBB, which is nothing but base to base voltage. We are applying a base to base voltage. This is nothing but the base to base voltage, and this is the polarity of the base to base voltage, and the peculiarity of this voltage is in such a manner that this will reverse biases. This is the N region now, this is P. So what happened, this region will reverse biases the whole N region. Am I right? Emitter is open, so no need to consider about P and all. It is actually not there, you consider, because emitter is open, no voltage is applied. So only we applied a voltage across the base. Basis is nothing but a long N bar. If you apply a P here, what will it make? It will reverse biases the whole N region. What it makes? It will reverse bias the whole N region, and due to that, there will be a large voltage drop across this region. Is it clear? And we know that, see my dear, this polar P, this is whole positive, and this will slightly, this forward biases this P, but the region between this P and B2 now, it is very shorter. So the majority of the resistance will be offered by the long N region, because I will tell you, okay, I will tell you once more. See, normally this working is slightly confusing, but if you understand this, it will be very easy. Listen my dear, don't go that much. Suppose I am applying a voltage VBB here. What happens? It will reverse bias the whole N now. So what happened? There will be high resistance in N, because when emitter is open, we have base is slightly doped, and emitter is heavily doped. Is heavily doped. A small leakage current will flow from P2 to E. See, when VBB is applied, that is nothing but the reverse biasing voltage. What happened, my dear? Considering this positive and P, what happened? There will be a chance of small forward biasing of P across this, so that there will be small reverse biasing current due to minority carrier will be flowing from this base to P. But since this is there is no terminal across the that means that there is no voltage we are applied or emitter is open, so no need to consider for that current, and there will be large voltage applied across, that means there will be large voltage drop across the whole silicon n-type bar. This voltage is represented by V1, because whenever reverse biases this whole n region, the resistance will be very higher. We know that whenever we reverse biases the whole n bar, what happened? The resistance, it is very high. The resistance by n bar is 5 to 10 kilo, nearly 5 to 10 kilo. So that much resistance will be there along this bar because it is reverse biased. Forward bias resistance is very much lighter or lower than the reverse bias resistance. We already know that. So what happened? This P and the whole N will reverse biases, so that there is an appreciable voltage drop across this whole N bar, which is nothing but V1. Okay. And now what happened, my dear? If we are applying a voltage now in the emitter terminal, what it will happen? What it will leads to? Okay, we will research. What happened, my dear? When a positive voltage is applied in this VE, so we will write here. When positive voltage applied on emitter, what happens? It makes this P to positive and this N will make like a forward biased condition, because emitter, it will inject large number of holes to the N region. Am I right now? If P and P gets opposed, because it is positive and here it is already holes as a majority carrier, this P and P will push more number of holes to this N region, and if the voltage applied or voltage VE greater than V1, if the voltage, there is a voltage now, due to reverse biasing there will be a voltage drop, which is nothing but the reverse biased voltage drop V1. If we apply a voltage VE which is greater than this V1, my dear, what happened? There will be a sudden flow of IE, and resistance suddenly drops. What it means? Suppose we are applying a positive voltage here in P, more number of holes will be what injected to the whole end region, and we are again increasing the voltage V sufficiently in such a manner that if that V is greater than the voltage drop across the N bar before V is applied, then what happened? If V is greater than the V1, what happened? The forward biasing will overcome the reverse biasing. The forward biasing will overcome the reverse biasing, so that there will be a more and more number of holes will be injected. So electron hole combination will take place. What happened? Electron will be directly falling. That means there is not so much holes now. So electron will be start combining. So the current will be flowing in such manner. So there will be base current and there will be large emitter current IE, because large number of holes are injecting due to VE. That VE should be greater than this V1, of course, which is greater than VBB, So what happened? A large current will be flowing. If the current is flowing, my dear, what happened? It will be tend to a forward biasing. And one more thing you have to note, this P and this base 2 now, E and base 2, this region is very small. So initially the resistance offered by this region will be very small without voltage in the emitter. But this P and the whole N, this region is very high. So you have to note one thing. Emitter and B2 region resistance is lower than emitter and B1 region because of emitter and B2 is close to each other. I will tell you. This emitter and base 2 now B2 is very close to each other, am I right? But this emitter and B1 is very long. So this much material is lightly doped material, this much length will be existing there. And only this much length will be existing in between E1 and B2. So whenever length increases, what happens to the resistance? R is equal to rho L by A. So L will be increasing, means R will be increasing. So the resistance between these region is very high. That is why majority of the voltage, that is VBB, is developed or dropped across this region. I didn't mark from here to here. Why? I only mark from here to here means majority of the voltage will be dropped not in between this but in between this, because in between this it is a very low area, low distance, so that resistance will be very less. But in between this to this, the length is very high, so that the resistance will be very high. So from this to this only we can mark exactly, if you want to know exactly from this to this. Exactly from this to this will be the, what my dear, this region to this region will be the V1. Is it clear? So what happened when we are applying a voltage VE here, due to the large number of holes injecting in the region, due to large number of holes injecting into the region, my dear, what happened? There is a flow of very high current IE in this region, and so that there will be a very high current across the channel happen, so that the voltage V1 suddenly fall to 0, because a large current is flowing, making the resistance to very low value. So whenever we can divide the operation as yes. Okay, here I will write. So without applying VE, without applying VE, my dear, without applying VE, there exists a positive, like this, positive resistance along the N channel silicon R. But when we apply a positive VE, the resistance starts decreasing on increasing VE. That means if you are not applying any voltage, means whenever we increasing the voltage, that much voltage drop will be there, that much resistance will be generated, because whenever we increasing VBB without applying voltage in the emitter region, whenever we are applying VBB and increasing VBB, means more and more reverse biasing take place across the N channel. But we are applying VE and we are increasing the VE, keeping VBB constant, my dear. VBB constant, we are increasing VE, means what happened? There will be a decrease in resistance across the channel, because this VE makes this PN as a forward bias condition. So whenever we are applying a forward bias condition, the resistance of the diode will become decreasing. So that is you have to note here, my dear. These two important things you have to note here. Without applying VE, there exists a positive resistance region along the channel, and when we are applying positive is EVE, that is this one, what happened? The resistance starts decreasing on increasing VE, that is negative resistance region. So that is what, my dear, we call it as negative resistance region. We call it as what? Negative resistance region. That positive and negative resistance region, these words now, these are very, very important. These are very, very important. Is it clear? So what happened finally? There is a flow of large current across the channel happens, and this piece of material starts conducting. This piece of material starts conducting. And what is the advantage here, my dear? We can make or we can alter the resistance of the channel. That is the main advantage. We can alter the resistance of the channel and we can control the current. We can control the current by applying the voltage here, by applying the voltage in the VE. Okay, let us discuss the characteristics now, so it will be more and more clear. It will be more and more clear. Let's go to the equivalent circuit. Things will be more clear then. Okay, and later on we will go to the characteristics. Equivalent circuit. Okay, equivalent circuit. Okay, so that's all. Listen my dear, so let us analyze with first thing without V. So if you are not applying any V here, what happened? The diode will be simply like a reverse bias. There is will not be considered this portion, right? So what happened my dear? I can write like, let this voltage be V1. Okay, let like this voltage be V1. So what will be this V1? V1 will be nothing but my dear VBB into RB1 whole divided by RB1 plus RB2. Let V1 will be equal to VBB into, I am taking this RB1 into RB1 divided by RB1 plus RB2 as eta. So V1 equal to VBB into eta. So this value of V1 is nothing but my dear VBB into eta, you imagine. And the eta will be vary from 0.5 to 0.8 because I already mentioned you more voltage will be dropped across RB1, not across RB2, because RB2 is the resistance in between the top B2 and the P region. So that is the length is very short there, so the resistance also very less there, but more resistance will be offered by the nearer region, I mean the lower region. That region is nothing but between the EB1 and emitter region. That's why RB1. Also you have to note one more important thing here. RB1 can be variable because whenever we are increasing the value of decreasing the value of VE, this RB1 also vary. So that is why it is represented as a variable resistor. That is why it is represented as the variable resistor. And this is without VE. Then what happened with VE? With VE, what happened my dear? The total voltage is, let it be represented by VP. It is nothing but VDD plus eta VP. So if you are applying a voltage, forward biasing voltage here, this is nothing but diode drop. That is normally 0.7 volt. In silicon material, it will be normally 0.7 volt diode drop. That means whenever the diode is forward biased, it is just a PN junction, not simply diode drop you can write, because that is simply a PN junction at 0.7, but this may be vary. So diode drop, it simply you can write. That is whenever the diode is forward biased, there will be a very small drop, that is called the diode drop. And this P is nothing but my dear peak voltage, peak forward voltage. Peak forward voltage. So this peak voltage VP will be equal to nothing but my dear, whenever we are applying VE, what will be the total? Apply KVL in this loop, that's all. Apply KVL in this loop. VE equal to, instead of V, you can see, you can represent VE also, no issue, no one will ask you. Okay, VE also you can write. VE also. VE will be equal to a small voltage VD plus eta VB, that's all. Eta VB now, that's all. Okay, simple, that's all. KVL apply, you apply just a KVL here. V equal to VDD plus eta VB. Is it clear? That is with V. When we are applying the voltage, there will be the addition of VD also, that you have to just know. That is the equivalent circuit. That is the equivalent circuit. And let us discuss the characteristics, my dear. That also very, very important. I will draw here. Okay, characteristics. IP and IE. Okay, saturation region, negative IP and VP. That's all, my dear. Listen, my dear. So this is the characteristics of a my UJT. So it is nothing but the graph between V and I. V, and that is the applied voltage across the emitter region plus the emitter current I. So the region is classified into three, my dears: cutoff region, negative resistance region, and positive resistance region. So cutoff region is nothing but, what is the cutoff region? Cutoff region is nothing but, my dear, see, the peculiarity of, even without applying any V is equal to 0, there will be a small current. There will be a small reverse current, leakage current. Even if at this point V is equal to 0, there will be a current. That is called the cutoff region. That means even without applying V, due to minority carrier, there will be a small forward biasing. Okay. In the P and N region, not actually forward biasing, it is a reverse biasing of P and N region, and there will be a small current due to minority carrier from B1 to P, B2 to P, from this region to this region, this region to this region. That is called the leakage current. That region is called a cutoff region, because we didn't on our UJT at that time. UJT act as an off switch there. And now, if you are slightly increasing the voltage, and when it reaches a value VP, that VP is nothing but, my dear, VE. Okay, it is better to use VP now here. If VE we are using, it is common. VE will be common. Total voltage will be VE. That V particularly equal to VP, then only the breakdown happens, right? So what happened? VP is nothing but this voltage. So at that point, what happens, my dear? That means whenever the applied voltage is greater than the voltage drop across the B1 and emitter. Voltage drop across the B1 and emitter. What happened? There will be large current flowing. The current is increasing very highly. See, the current is increasing very highly. At the same time, the voltage of V drops to very low value. That peak value voltage is called P. VP is nothing but a peak value of voltage. IP is the peak value of current. This is nothing but, my dear, this is nothing but valley voltage. This is the valley voltage, and this is the valley current. IV is the valley voltage, and VV is the valley voltage, and IV is the valley current. That is the lowest current. And after that, there will be saturation. Because a large number of current is still flowing on the device, and that current will be actually restricted by the power supply only. Whatever the capacity of the device and whatever the capacity of the power supply, that much time the current will be flowing. So it is determined by the saturation current will be determined by the supply only. So this is the saturation current, and there will be a small increase in the voltage, doesn't mind. So the current will be goes on increasing. That is limited by the power supply only. That region is called the saturation region. Is it clear? And one more interesting, same characteristics can be drawn with the IE, that is nothing but, my dear, VE. So particular value of VE, that means VB1, suppose VB2, suppose VBB3, VBB2, VBB1, because at a particular value of only this can be drawn now. At a particular value VBB only this can be done, right? So whenever we are increasing, where VBB3 greater than VBB2 greater than VBB1, when we are increasing the reverse biasing voltage here, what happened, my dear? More peak voltage is required for turning on the device. That will be VP1, will be VP2, and VP3. The voltage to turn on the device will be increasing whenever we are increasing the reverse biasing. So how much controlled it will be here now? How much voltages can be controlled by simply varying the resistance, the voltage VB and the forward biasing voltage VE? That much range of voltage can be controlled. So when we are increasing the voltage across the reverse bias, more will be the peak voltage Vp. That's all. More will be the peak voltage Vp. So that's all about the UJT, and where it is applied, my dears, applications. First of all, timing circuit. Next one, sawtooth wave generator. And trigger circuit. So these are the area where this UJT can be applied. Is it clear, my dear? Is it clear? So that's all about the UJT.